Hello guys, let's start with our very first lecture on psychometry. It is mainly important for GATE aspirants as well as for other agricultural engineering based examinations. This is brief introduction about me. My name is Maya Sharma. I am a PhD scholar in College of Technology and Engineering, Udaipur, Rajasthan. I have secured 78th rank in GATE 2014, and here it is my mail ID. Today we are going to discuss about introduction of psychometry, the different properties of psychometry or psychometric properties, weight bulb temperature, the need or the importance of weight bulb temperature, and how to read the psychometry chart. We are going to discuss it in this lecture. The different psychometric processes like cooling, humidification, heating, drying, etc. And application of psychometric properties in food processing. And what are these applications? Mixing of air stream and drying. There can be another applications as well, like evaporation, etc. And next term we are going to discuss here is the bypass factor, and on final slide we have two numerical questions. So psychometry, it is the study of thermodynamic properties of moist air. What are these thermodynamic properties? These are like temperature, specific heat, enthalpy, entropy, etc. And here we have used the term moist air. Why? Because in our environmental air we have dry air as well as water vapor. So we are considering also the study of thermodynamic properties of moist air is called as psychometry, and these different properties of moist air are termed as psychometric properties. Here we have considered a fixed volume of environmental air which consists two elements as dry air and water vapor, and we have named its specific volume and mass, etc. So before going to the psychometric properties, what is dry air and moist air, let's see that. So dry air is combination of mixture of gases. What are these gases? These gases are oxygen, nitrogen, carbon dioxide, H2S, NO2, etc. And the molecular mass of dry air is 28.966 by considering just nitrogen and oxygen. And gas constant for dry air is 287 joule per kg into Kelvin. It is calculated using PV equals to nRT equation by putting all these value and atmospheric pressure. And the density of dry air is 1.293 kg per cubic meter. So now what is moist air? Moist air is the mixture of dry air as well as water vapor. So in our environment we find the moist air, not the complete dry air. Saturated air we termed the environmental air as saturated air when the absorption of water vapor into dry air has reached up to its maximum limit, right? So mixture of dry air and water vapor, when the air has been diffused the maximum amount of water vapor into it, means after this limit, when we add a little amount of water vapor into moist air, then this water vapor will form droplets. So now let's start with the psychometric properties. First term is dry bulb temperature. It is the actual temperature of moist air is called as dry bulb temperature. Means when it is stated that drying temperature is this much, evaporation temperature is this much, air is at this much temperature, so that temperature is termed as dry bulb temperature. And what is wet bulb temperature? It is measured when air is passed over weighted sensor tip of bulb thermometer. And so we will see in the next slide what is the importance of this wet bulb temperature. Next property is dew point temperature. What is it? And the temperature at which the water vapor begins to condense is called dew point temperature. How can water vapor begins to condense? There can be two possibilities. There can be two possibilities. One is when we add water vapor into moist air, and after reaching its maximum limit or saturation limit, when we add some more water, then that water vapor will form droplets, right? And what is the another method? We are not adding any water vapor into it, but we are lowering the temperature of moist air so that the water vapor present in moist air can be converted into liquid water. So that temperature is termed as dew point temperature. And so this phenomena can be seen while we are taking out the bottle from refrigerator, and we find that there are droplets on surface of bottle. Next psychrometric property is specific humidity. It is nothing but the amount of water vapor present in 1 kg of dry air is termed as absolute humidity or humidity ratio. So I call it as the moisture content of moist air on dry basis, right? It is similar to that, like dry basis, moisture content on dry basis. So it is formulated as mv divided by ma. mv here is the mass of water vapor and divided by ma, mass of dry air. When we put the values of mv and ma using the PV equals to nRT equation, we find H equals to 0.622 into PV divided by PA. PV here is the partial pressure of water vapor and PA is the partial pressure of dry air. And by Gibbs-Dalton law, we know that when the total pressure exerted by mixture of gases is the sum of partial pressure exerted by each component of that mixture of gases, right? So here we have the two components in a mixture, water vapor and dry air. So the total pressure exerted by the moist air would be equals to PA plus PV. So here we can write the PA as P minus PV. P, capital P here is the total pressure and PV is the partial pressure exerted by water vapor, right? So finally we found the humidity, the formula of humidity in terms of a single unknown factor. Next psychrometric property is relative humidity. It is the ratio of vapor pressure of existing moist air to saturation vapor pressure at the same temperature and atmospheric condition. It is denoted as phi, and it is formulated as PV divided by PS, means the partial pressure of moist air divided by the partial pressure of saturated air, right? Next property is degree of saturation. As name suggests, that it is ratio of absolute humidity of given air to the specific humidity of saturated air at same dry bulb temperature. Means the humidity of given air divided by humidity of saturated air. So mu equals to H divided by HS. And what is the formula of H? H is the 0.622 into PV divided by P minus PV. Or for saturated air, HS would be equal to 0.622 PS divided by P minus PS. So here we can find the relationship between degree of saturation and relative humidity. So the next psychometric property is humid heat. It is the amount necessary to raise the temperature of 1 kg of dry air and its accompanying water vapor by 1 Kelvin. Here means the heat required to raise the temperature by 1 Kelvin for a 1 kg of dry air plus accompanying water vapor. It is like specific heat. It is similar to that specific heat of some materials. So it is so in our moist air we have the dry air as well as water vapor, right? So for dry air we know the specific heat. It is 1.005 kilojoule per kg in dry air, and for water vapor it will vary according to the humidity. So the total humid heat for moist air can be Cs equals to 1.005 plus 1.88 into H kilojoule per kg dry air. Next psychometric property is humid volume. Humid volume is the volume of 1 kg of dry air plus volume of vapor in it at 1 atmospheric and given temperature, right? And the VH is formulated as 0.00283 plus 0.00456 into H multiplied by TD plus 273 cubic meter per kg. Here TD is in degree Celsius. And the next property is enthalpy of moist air. Enthalpy is total heat in or the total heat of moist air. Moist air means air and water vapor mixture. So at any temperature we have the sensible heat of moist air as well as the heat of vaporization of water vapor, because water vapor is in vapor state. So here we would have the H equals to sensible heat plus latent heat of vaporization. So H equals to Cs into Td plus lambda into H. Here we can put the value of Cs, which is 1.005 plus 1.88 into H multiplied by Td, and the latent heat of vaporization of water is 2504 into H kilojoule per kg. Next, here we have wet bulb temperature. There are two types of wet bulb temperature: thermodynamic or adiabatic wet bulb temperature, and another one is the psychrometric wet bulb temperature. So adiabatic wet bulb temperature, for measuring this adiabatic wet bulb temperature, first, what is the adiabatic wet bulb temperature? When incoming air passes over a water surface and it leaves its saturation state, the temperature of that saturated state of outgoing air is termed as adiabatic wet bulb temperature. This air, in this process, there is no incorporation of heat from the surrounding, right? So this is termed as adiabatically. What is written here? Moist air is adiabatically saturated by evaporating water. The latent heat of vaporization is needed to bring the moist air of state 1 to saturated state 2 is supplied by sensible heat of incoming air. What happens while measuring the adiabatic moisture, adiabatic wet bulb temperature? We take a very long pipe which is half filled with water, and air comes or air passes over this water surface and it leaves in saturation state. So the humidity of the outgoing air is equals to this saturation limit, and so for measuring this adiabatic wet bulb temperature, we need a long pipe, right? And how this process happens, the evaporating water, and this evaporated water comes into this diffuses into the incoming air. How does it happen? This air at some temperature, at some dry bulb temperature, the incoming air has some dry bulb temperature, so it has some sensible heat. This sensible heat is transferred to the water surface, so water surface gets some energy, and this water converts into the water vapor, which is diffused into the air and make this air as saturated. So it is written here that the latent heat of vaporization needed to bring the moist air of state 1 to saturated state 2 is supplied by the sensible heat of incoming air. So both the sensible heat would be equal to the latent heat of vaporization. So here we have mentioned it as Cs into T1 minus T2 equals to lambda saturated multiplied by H2 minus H1. And so we can find the T2 temperature, or the temperature of outgoing saturated air, which is termed as wet bulb temperature. So it is equals to T1 minus lambda saturated multiplied by H2 minus H1 divided by Cs. Cs is the specific heat or humid heat, and lambda saturated is the latent heat of vaporization. So next is the psychometric wet bulb temperature. What happens in adiabatic wet bulb temperature? And we need a long pipe to make the air completely saturated, right? So here we have solution for that. What is happened here? And the bulb of thermometer is covered with a wet cloth, and moving air is passed through this wet cloth and leaves at some higher humidity ratio, right? So it is written here, it represents the temperature at which water evaporates and bring the air to saturation, and the thermometer with wetted bulb gives the equilibrium temperature, is called as wet bulb temperature. This temperature is lower than dry bulb temperature but higher than dew point temperature. We'll see during the psychometric chart reading that how this wet bulb temperature is measured by reading the psychometric chart. So this covered cloth or incoming air takes moisture from this wetted cloth and leaves at higher humidity. It is not necessary that it becomes completely saturated, but when the temperature difference of inlet and outgoing air is higher, then this diffusion of water vapor into air, the rate of diffusion of water vapor into air becomes higher. So here we have mentioned as the H into A multiplied by T1 minus TW divided by lambda W is equals to the KY into A multiplied by HW minus H1. Here we have used the mass diffusion concept. So the final temperature of outgoing air, or the wet bulb temperature, psychometric wet bulb temperature, can be written as T1 minus KY into A multiplied by HW minus H1 divided by small h. What are these different constant? Small h is the heat transfer coefficient of air. Capital A is wetted surface area. Wetted surface area. And that the Ky is diffusion coefficient of water vapor through the air film and water vapor mixture. So we have seen that when the outgoing air using the psychrometric wet bulb temperature becomes completely saturated, then this temperature would be equal to the adiabatic wet bulb temperature. So we can compare these two equations at saturation limit, and we find the Lewis number, etc. This is higher study. Next we have psychometry chart. All these psychometric properties are presented in a graphical manner for air or different cases. It can be in the case different, the mixture of different gases and water vapor or atmospheric air. Generally we use the psychometry chart at atmospheric pressure, and this psychometry chart consists 8 psychometric properties. These are First line we have dry bulb temperature. From left to right, it is showing the increasing values of temperature. On complete psychometry chart, we only have these horizontal lines for temperature representation, right? And this vertical line shows the humidity ratio. And what is humidity ratio? It is the mass of water vapor present in 1 kg of dry air. These inclined lines shows the wet bulb temperature and enthalpy as well. There is slight difference in inclination of enthalpy and wet bulb temperature, but in generally we assumed both as on a same line, right? These lines shows the relative humidity. Here we have 5%, 10%, 20%, 50, 80, and this line shows the 100% relative humidity. And we have these lines, the sharp inclination. These lines shows the humid volume of moist air. And what else we RH line, dry bulb temperature, humidity line. So yeah, these are the lines for lines on psychometry chart. So how to read these lines? Let's see. Here it is the different psychometric processes. Here we have temperature lines, and these are the humidity ratio line, and this is saturated line, right? So when we go with higher temperature without any change in humidity, we find that only the temperature is changing, so it is denoted as sensible heating. Only the temperature is changing is termed as sensible heating, and the reverse of sensible heating or the lowering the temperature we find as sensible cooling. Means we are just reducing the temperature of moist air. And what happens when we increases the moist water vapor in moist air? Humidification takes place. So there is no change in temperature, just we are adding water vapor into the moist air, and it is termed as humidification. The opposite process of humidification termed as dehumidification. Here we have to note that there is no temperature change, right? And while we changes the temperature, the increased temperature and increased humidity is termed as heating and humidification, and opposite to that while lowering the temperature as well as lowering the humidity is termed as cooling and dehumidification. And what happens when we reduce the temperature but increase the humidity, that is termed as evaporative cooling. Or in case of drying, this similar process happens. What happens in drying? The temperature of outgoing air reduces while the humidity increases, and opposite to that we have chemical dehumidification. So in our next slide we have application of psychometric properties in food processing. First application is mixing of air stream. For example, when we take the example of multi-effect evaporators, where the water vapor produced from first effect goes to the second effect, as well as some amount of fresh steam is also injected to the second stage. So mixing of air is taking place. So what happens, how the mass balance, energy balance is taking place in mixing of air? Let's consider that. So here we have denoted the stream 1 and stream 2 and different mass or heat denotation, heat notations. And so this process, the mixing of air streams, is also shown here in the psychometric chart. So when we do the total mass balance, where the stream 1 and stream 2 are making the stream 3, right? So m1 plus m2 is equal to the m3 mass of air stream of first air stream plus mass of second air stream is equals to the mass of third air stream. And we do the when we do the water vapor mass balance, then we find m1 into h1 plus m2 into h2 equals to m3 into h3. And now here we can find the humidity ratio of mixed air as h3 equals to m1 plus m1 into h1 plus m2 into h2 divided by m3. Here we can put the m3 as m1 plus m2, and when we do the energy balance, we find m1 into h1 plus m2 into h2 equals to m3 into h3, and the enthalpy of outlet air is formulated as h3 equals to m1 into h1 plus m2 into h2 divided by m3. And here also we can we can put the value of m3 as m1 plus m2. And as we know that the enthalpy of moist air is Cs into Td plus lambda into H, so we can put this enthalpy for stream 1 and stream 2 as well as for the stream 3. Finally we find the outlet temperature. The temperature of outlet air is as m1 into Td1 plus m2 into Td2 divided by m3. Td1 and Td2 are the dry bulb temperature of stream 1 and stream 2, right? Next application we have drying process. Drying process in convective drying of food material follows adiabatic saturation process. We have discussed the adiabatic saturated process earlier. And as the drying air passes through the wet grain mass, a large part of sensible heat of air is transferred into latent heat of vaporization as a result of the increasing amount of water held in the air as vapor. As we have discussed earlier, that how this drying process is completed, right? Next, here we have another term, bypass factor. What happens when during heating or cooling of air, the air is passed over a cooling or heating coil, then some amount of air bypasses without affecting its temperature, right? So the term incorporates as bypass factor. What is it? When air passes over a coil, some amount of it bypasses without affecting, while remaining comes in contact with coil. This bypass process of air is measured as bypass factor. So the bypass factor for heating coil is given as TD3 minus TD2 divided by TD3 minus TD1. The TD1 is the dry bulb temperature of inlet air, TD2 is the dry bulb temperature of exit air, and TD3 is the temperature of coil. And similarly, the bypass factor for cooling coil is calculated as TD2 minus TD3 divided by TD1 minus TD3. And in our last slide, we have two numerical problems. First one indicates that the values of absolute and saturated humidity of air in a room are 0.022 and 0.04 kg H2O divided by per kg of dry air respectively. What are the values of partial pressure, partial water vapor pressure, saturation water vapor pressure, relative humidity, humid heat and humid volume? सिंपल है. हम इसको we know that humidity is termed as or is calculated as 0.622 into PV divided by P minus PV. So here we can find the value of PV and PS using the humidity formula. And relative humidity is the when we have calculated the partial pressure of water vapor and saturated water vapor pressure. So using both these value, we can find the relative humidity. Humid heat, we have the formula as 1.005 plus 1.88 into H. So we can put the value of H and we can find the value of humid heat as well. Humid volume, we have the formula for humid volume also. Another problem says, in grain dryer, one stream of air at 50 cubic meter per minute at 25 degree dBT, it's dry bulb temperature, right, is mixed with another stream at 50 cubic meter per minute at 60 degree Celsius dry bulb temperature. Find the dry bulb temperature of mixer. Easy है, right? हमने पढ़ा था mixing of air में the temperature of outlet air can be calculated as M1 into TD1 plus M2 into TD2 divided by M3. So the answer of both these numerical problems are given here. You guys calculate all these values and find your answer and match your answer, right? And one more assignment I can give you. Search the highest location where humidity ratio is highest in the world, right? And another where the location where the humidity ratio is lowest in the world. And these are interesting facts, right? Like similarly, you can find the highest vapor pressure, the location of highest vapor pressure exerted, and similarly the lowest vapor pressure exerted by atmospheric air. Similar facts, interesting facts you can find out. So thank you. Let's we'll see you in next lecture. Thank you. All the best.